From ContainerDays Hamburg, this video is proudly presented by DAX IT.
Yeah, thank you very much. I usually could also add a few more things, like I'm organizing the Cloud Native Summit in Munich and the meetups there. And also published last year a book about platform engineering for architects with two lovely co-authors from ContainerDays and Red Hat. So if you would like to know more about platform engineering itself, I can highly recommend that. Today we're talking about IDP, AIDP. The idea behind it is like, are we somewhere on the convergence of like platform engineering and AI? Why do we need to think about it? Well, I will give a detailed answer throughout the presentation, but in short, practically the whole cloud native universe with all its tools slowly drift into the direction of AI and supporting everything around it. Is it about the pipeline automation? Is it about inferencing, serving workload, routing requests, caching, storing models, and so on and so forth? We see that the cloud-native universe going to be an AI-native universe. And if you look at the typical huge landscape of the CNCF, we know there are hundreds or even thousands of tools waiting for us to find somehow a way into AI. So what do we think about AIDP? And there are actually two directions we can think about. The one thing is an AI-powered platform, and the other one is an AI-enabling platform. Enabling means that the platform itself helps us to train models, deploy models, but also integrate applications with LLMs. And this turns out to be one of the largest challenges right now. If you have seen the very new MIT research on how many AI LLM projects are failing, it's over 95%. That's a very critical number. However, we need to take care of this research. It's, well, scientifically spoken, not a good research because they just interviewed 156 companies, which scientifically is not enough to actually define a good evidence. The other part is the AI-powered platforms. And AI-powered means like we put AI in the places where it helps developers to start projects, document their projects, and so on and so forth. No matter which direction a platform takes, and it can also take both directions, it always has actually 4 and even more targets that it wants to achieve, like accelerating the development cycles, help us in improving the code quality, being more productive, and reduce the operational overhead. I think that's points that you read and see everywhere when we're talking about, oh, use more AI and all your problems are solved. I do not want to discuss today if that's true or not. I've seen and worked with my team on evidences where I can say like, yes, it can improve. But I also have seen enough projects where I say like, it's more a problem sometimes or most of the time. So my point for today is to help you to think about a little bit like how we can bridge the gap between the traditional classic software development on the one hand side and the AI engineering on the other hand side. And AI engineering can be also machine learning engineering, but technically we are then talking actually about two different domains. Right? So if we talk about machine learning, we talk about training models. When we talk about AI engineering, we are talking about integrating models to make it useful for any kind of end users here. So what is therefore very interesting or relevant is to think about that we have to change a little bit the way how we integrate and build things. The good old DevOps cycle, which was carrying us through the last decade, is a little bit outdated because reality looks more like this. It's slightly become more complicated. It's not one infinite loop. It's, I don't know, 3, 4, depending on how you put the infinite loop. But this is more or less showing the kind of reality we have to deal with, right? We have to take care about data and data sets. Everyone knows shit in, shit out. The same thing with LLMs. If you give them something stupid to eat, they will give you also some stupid answer. Simple as that. If you train them on stupid data sets, you will get very poor models. And this is the same for fine-tuning and whatsoever, right? So We need to take care about the data stuff. It must be good. It must be high quality. That's why this is their own market. That's why there exists companies earning hundreds of millions of dollars providing you with good data. Because the internet is full of, exactly. DevOps, we know. And this is actually the beauty which we need to think about it today, that it becomes somewhat more complicated to provide applications that integrate with LLMs. On the other hand side, I found it interesting, not because of the AI part, because finally something happens, something new in this environment, right? It's not continuously deploying new web applications and building some backend service and discuss the 500th time if a database should run on Kubernetes or not. Now it's a question if a vector database should run on Kubernetes or not. So discussions are shifting, and that's actually what makes the whole topic a little bit more interesting. So I often get asked, like, okay, how this should look like. What are actually the AI engineers are doing? And first question to you. Who of you is building a platform that's serving AI? Good amount of. And who of you currently has problem to drive the adoption within your enterprise or company? 1 to 3 people. The rest is living in a beautiful world. So we try to always explain to our customers, look, there's a lot of stuff going on. It's not just like the application part where you have to integrate the models and all is good, because it becomes very complicated. But there's also parts where we have to take care about the model itself. And a lot of companies miss this part. So I shortly will, and it's not about length views, but I shortly would like jump into length views because it maybe helps to understand one of the end users of an AIDP, which are the engineers who take care that the model, even if they have shit in, do not have shit out, right? So length views, also an open source tool developed by a very cool team from Berlin, comes with practically all batteries included to take care about prompt engineering, seeing how evaluation is going on, and so on and so forth. Again, it's not about the tool. I will just very shortly give you some taste what you're doing with this tool. So when you get started, you get, for example, some ideas about like the traces which are going on, how much the current costs for the models are, and you see some scoring about different processes, I would call them, and how good the answers of the system is in this case. So if I would like to know more details, I can jump right into some traces and getting a little bit more information, if the internet is super slow, and see what's going on, how long which part of the communication takes. I can see the request here on the right-hand side, for example. I can see the output and a few more of the metadata. We can also break this down to sessions or even for users, right? And now some people might scream and say like, what? Users? We're in Germany, we cannot track users and whatever they are doing in an AI system. Well, GDPR, flush it to the toilet because of the EU AI Act. You have to track every prompt that an employee of your company is doing. And you also have to track what the AI is answering to it. Because of PII leakage, because of maybe some dirty answers, maybe because of some dirty requests, whatsoever. You have to do that in some cases, or most cases. So very relevant to have also an overview into this one. If you're in the engineering part, you can, for example, do some versioning of the prompts. So if you're not really, familiar with how that all works, usually you explain a system before what kind of answers you're expecting. And this model with this preloaded mindset in some way will then, on the user's request, answer in a specific way. But you have to test this, and you can see here that someone has changed continuously the prompts until you found a perfect pre-configuration for those prompts. For sure, you have a playground for testing all the things out. And then you have a few other things like LLM as a judge. So you use LLM to actually evaluate practically the answer of another LLM. Sounds a little bit stupid, I know. But sometimes you cannot do this in a large scale. in another way. You have to use another AI to tell me if the answer which comes up there is the right thing I'm waiting for. And then you have to also you can also manage, for example, data sets and so on and so forth. Nevertheless, this is just to give you a very, very short introduction, like what are people doing actually with all this LLM AI thingy if we are in an enterprise context and if we provide our own models to our own customers, right? And this is one end user which we have to talk about. But there's absolutely more in it. So we maybe talked about, somewhere this rear end of all of the life cycle. But for sure, we need to think about like where to store the models, how to put the hardware there, how we distribute it, how we integrate it into the application. We need to think about the model caching, how to monitor all of that. In the Kubernetes world, that's easy peasy. We have open telemetry. This brings us most of the information. And from there, we can put up a few other things like open LLMetry. Also, there's a few discussion about that people do not like to come to the point that they have to use the SDK of it and so on. Nevertheless, there are options, and our cloud-native space brings us almost every answer for the operational part. If we go more further, for sure we have on the one hand side, take care about everything which is below. Different architectures that are relevant for serving our models. And we had recently a discussion about it, like, hey, why do we need GPUs? And then we have an MPU and a TPU, and why we need DPU for all this stuff? Well, because all of these different architectures are built for different tasks, right? And also, not always is GPU the right answer for your AI question. Sometimes you have to massively distribute a request, put some pre-processing part on a CPU because it's nothing where you need a GPU for, while on the other hand side, you put some stuff in a GPU, but then you maybe have to split even the request to be faster on the pre-filling and the decrypting part, and so on and so forth. And in the other direction, we have obviously for all the AI landscape within the cloud-native ecosystem, a lot of answers which we can work with, and that we have to implement into an IDP to make it valuable for an AIDP or help companies to serve in a better way AIs or use AI better in their daily development. And to answer the question of like, are we on the convergence between platform engineering and AI? These are almost all tools, and I think there are even more, that we can see within the cloud-native space or beyond that, very related or very closely related to the open source foundations, that are relevant to help us serving AI. And that's a lot. It's really, really a lot. If you take a look back 2 years, this was tiny. It was just a little bit. There were just like first ideas, how we can use this and that, how we can change that and that. But we have seen very fast, like Kserve has moved from a serverless engine to an inference service. We have seen Envoy proxy not just being a proxy, suddenly it becomes an AI API gateway. And so all of these models start moving, or not models, all of these tools and all of these components start moving into different directions, as long as they're AI written on it. And I can understand, because they get money for it, if AI is on. So sometimes it makes sense and keeps also open source tools being developed. But nevertheless, the landscape becomes big. And that's a very small one. If you want to see a fun picture, there's the MAD map. MAD is like machine learning, AI, data engineering map. From 2024, maybe 2025 is on it. There's thousands of applications and commercial products on it that all do the same stuff like this one. It's crazy if you take a look on it. And then compare it to the previous year, the landscape is exploding. Okay. So there are a few things where we always should start with. Few things which we need to master if we really want to go the next step, if you have an IDP, to evolve into something that helps AI teams to do better work and not just do so-called ad hoc deployments. Also, that's not really ad hoc, but we see it like this because it's like a more AI focused rather than serving focused perspective. The first thing is we're talking about ML ops. Nowadays, you could call it LLM ops, AI ops, however you want to call it. It's just about like helping to orchestrate and manage and scale all the needed processes within the platform for the AI teams, in short. You also have to talk about the lifecycle and the orchestration of AI workload, because AI workload doesn't behave like the traditional application in some way. If I put out there a web application and I have 10 users, no big workload. It scale up to 100 users, no one cares. 10,000 users, okay, maybe I need a couple of replicas, but frankly speaking, no one cares. You do the same thing with the model, the credit card of your boss is burning like hell. If you scale up from just a few hundred users to a few thousand users, you literally have to spin up a decent amount of additional servers, GPUs, however, and whatever you use. It also depends on, like, obviously, which model, which GPU type, and so on and so forth. If you, I don't know, set up one node with the newest Blackwell GPUs, maybe one server is enough to catch your entire company. If you have an older A100 and you can not do a lot of the magic, which is possible nowadays, then you maybe need a couple of servers. In the end, it's becoming expensive the more people are using it. And yeah, this actually let us also directly talk about how to use and manage hardware, especially hardware for AI workload. So if you have never seen that, actually I try to, if someone has the possibility to get that thing, I would like to have it as a picture in my living room, you know, but with a real processor, it would be fantastic. That's NVIDIA's latest Blackwell, the holy grail nowadays. I think if you want to have it on Amazon, it costs like 80,000 per month, something like that. So it's a pretty powerful little thing, and it looks actually kind of beauty, I would say. Nevertheless, what we can all do with that and what we have to take care about and which possibilities do we have to use this hardware? Well, the old classic way would be to use, for example, virtual GPUs, which means that we take the GPU and just split it and share it for multiple pods or multiple virtual machines. That's the old world. We also have the MIG, the multi-instance GPU usage, as well as the GPU time slicing. Both works well together, right? So MIG is just like the hardware way of separating and slicing a GPU into some pieces which then can be redistributed about different applications. And time slicing, do nothing else than that. It literally slices the available time of the GPU into different time frames and distribute it to different applications and so on and so forth. Last but not least, I've added there also CUDA. It more or less kind of makes the same thing like a GPU time slicing, but it's an entire framework. It's not just like there for distributing the workload. It has an SDK, a CLI, different tool components which you can deploy on top of it. It's an entire management suite, right? Nevertheless, because it also comes from NVIDIA, you need to list it up because it literally helps to distribute your workload perfectly. But it's an all-in match. If you go all into CUDA, then you're all in CUDA. You need to forget a little bit about the rest of the world. So what we can do if we have a physical GPU, you can see there in green, for example, the annotations for an NVIDIA GPU with 2 and an A100. What this practically means, this claim would cause that you take 2 entire GPUs for you. That might be a lot. If you do MIG, you can see it here. You take one slice of a current MIG. You still use an A100, but depending on how the MIG is configured, you will just get one, let's call it thread in this way, just to make it like that you can sync it. This one will use way less resources than the first one, right? And maybe it's the right thing to do. I don't know. It depends on what you're working, but normally it is a good way. Now, if you take time slices or add time slices, you do a GPU shared, and you can tell how many replicas you need to have in the device plugin. So this will like literally split up the available GPU, right? In this case, again, with a physical GPU. And you can do also this magic again with a MIG, so that you literally slice and dice it into very biteable little pieces. Why this is so important to spend so much time on it and even go more deeper into this is very just high level for this topic is GPUs are still extremely expensive, and we expect that in the next years they will become a very limited resource for a few political reasons, resource reasons, energy reason. There's a good amount of reasons why in the next years we cannot order them like cookies nowadays. It will not, most likely will be not that much possible. And this approach also come, or all of these approaches come with a couple of problems about the GPU support. So you can just support within one system one kind of GPU. You cannot really share it across servers. There are some ways to do that with Kubernetes and overlays and so on, but it doesn't feel native. It doesn't have a direct connection. A few things fall out, like MPS integration for the multiprocess service and the dynamic MIG provisioning. I had to update that. It's now supported. So also good that something is moving in this direction, right? And you cannot go for any other drivers in this app setup. So you have always the need to go with NVIDIA. That doesn't seem to be always a problem because most of their stuff is open source. But for example, some larger research center, they develop their own stuff for different purposes, and then it's problematic. So dynamic resource allocation comes into the game. With Kubernetes 1.34, it's now generally available also after a couple of years being in beta. And this allows you practically to do everything what we have talked before, just in a Kubernetes style, being very dynamic in allocating and adjusting workload to different slices, to different amount of GPU resources, which is very nice. And it allows you the cross-node resource claim. This means if one node with a GPU is completely overloaded and the other one is idling around, Kubernetes will take care that you get this GPU resource and your workload doesn't need to wait until the other GPU is free. And that's extremely helpful if you're in an organization where you would like to take care that your resources are probably used. Similar like before, we again do kind of a resource claim. We still talk about the GPU.NVIDIA as a resource claim class. And then we can see that, for example, we do a claim for GPU 0 and 1, so that we are telling practically kind of flexible or need multiple of those. And then in the pod, we again just tell like, okay, give me one of the GPUs. I don't care which one, right? And then we get shared access and Kubernetes takes care about the rest. This is the one part. Then this leads us back to this beautiful picture, because we have to think about, okay, now we literally just touch the bare minimum of how we can enable an organization and what we have really to think about to enable them. And this whole life cycle, this could be shown in this example. That's a little use case from one of our customers, a little bit changed in a few points, which practically shows I can use a lot of stuff of the cloud native universe for doing and training models and adjust them based on event triggers, for example, with new inputs and so on and so forth. What could be this input is like if you have a front end, like in Streamlit, and you have a user which says like, I like the input, or even give more feedback to the input, then we can reuse this for training it. The whole thing is then running obviously on Kubernetes, and the entire setup is deployed by Argo. And then we can extend it and use, for example, OpenLLM or another AI front-end part or VLLM to serve more models, but use also the previously provided data set. Again, that's a very simple ML ops lifecycle in some way. For me, the important message is there's just a few little components that are new to this lifecycle, but all the other stuff is good old cloud-native world. Another perspective on it would be, for example, for the Kubeflow part, right? So Kubeflow itself, built around MLflow in the end, is a very mighty tool. And if you use Kubeflow with PyTorch, then you can start training your own models. It's a native integration between both. The one's taking care about all the training, about provisioning, about orchestrating, and so on and so forth. But for a platform, you don't need the entire ecosystem. You can also start with a few little components in it, like the kubetrain or the Kubeflow training, the K-serve, and the model registry. Those are the little things which you also need if you just do fine-tuning. And that's where most organizations at the moment are more heading to. They don't need 5,000 nodes of GPUs and build their own model. This doesn't make sense. But you take something which is open source and throw in your own data and retrain it. You fine-tune it. And for this, you also don't need the entire setup. It's enough if you have a few little components which are simple to serve or simpler to serve than the entire ecosystem. It still might pull up PyTorch because it's the de facto tool or de facto standard tool in some way for training models. There's for sure others, but like you very fast always end up at PyTorch. The good thing is Kubeflow will take care about this entire process, right? You just need to give a little bit like, okay, what are the endpoints, where I should store it, where I get my data from, which base model I should take, and then I will do the magic for you. Simply spoken, it's someone who's doing ML engineering all day long most likely would kill me for that. And then from there, we have to move on for general inferencing, or the inferencing of some services. I still didn't find the right naming for it. Inferencing itself feels also a little bit wrong, because in the end, it means like I take a couple of inputs and I produce some information, something useful for an end user. But if I'm serving you a model, what is it then? In the end, it's just running an application, I would say. This picture comes actually from the Envoy community, I believe, how they integrate the Envoy AI gateway with K-serve and VLLM to serve models for certain organizations. And it looks actually kind of complicated because there's a lot of boxes in it. So we can simplify that in some way. I hope it's simplified. We still talk about the Envoy AI gateway. Why this is helpful is because it can help you to send requests off to different models. So you do not need always to pay the most expensive model. For a simple request, you use a simple model. For a complex request, you use a complex model, yada, yada, yada. What is important for the serving or for the inferencing? For me, the first time building an app for a customer, it doesn't felt so much complicated in some way because it's all cloud native universe. Right? You install it, you do your usual configuration, you have extremely expensive hardware, but magic is done because I don't take care about the rest of the workload. Right? The workload gets served and implemented somewhere else. But there were a few points in it that we afterwards really had to take care about, and which comes to a complicated point, like for example the KV cache, because it's a relevant part for improving performance. And this is also like the last few things which I want to fast give to you because I think I'm shortly running out of time. Model caching, for example, is very, very relevant if you do something with serving the LLMs to your end customers. Because this first part of the init container, getting the model and loaded into storage and started up, can take a lot amount of time. There's a few models that just like laying around is around a terabyte. And to load them, it's not like, snap, my container is loaded. It's like, pull, I go to my coffee machine, grind the coffee, put it into the coffee machine, make it, get my espresso out, make my milk, right? It takes ages to load that. So we want to get rid of this one. There's different way to do model caching. You just can do the good old way in Kubernetes and cache it locally with a container. Simple as that. But there's also a few, like Kubeflow, for example, has also the possibility to define a model caching. The other thing is about prompt caching. And also here, a lot of people just go for the Bainaked KV cache. It has just a problem. It grows incredibly fast. So we're talking about here like 10,000 tokens needs 16 gigabyte of storage. 10,000 tokens is not that much. A million tokens, that's a lot. That's where you can feel comfortable with and can do all kind of different stuff with. What is it? 1,628 gigabyte of KV cache. That's not a cache, that's a database, right? It's a huge monster. So our learning is go with LM cache. It's growing way slower, but it keeps with the same speed. And you can see, for example, if you use LLM cache with a VLLM together, you can have a way better or way faster rate of answering. So TTF is the first token, or time to the first token, which is answered for a customer. And you can see how much it literally improves just using cache. Another thing which we found out is like disaggregated serving, and that's really, really naughty thing deep into like how, for example, NVIDIA GPUs are working. But you always have like a process where you first pre-fill and then you decode your requests. The problem is that this pre-filling is extremely compute bound. It almost needs no memory or anything else. It just needs compute capacity, while the whole decoding needs a lot of memory. So what they found out is like, okay, let's split it up. 2 GPUs, one does prefill, one does the other part. We are way more faster in it. How much faster? A lot. That's a stupid technique, but it's extremely difference between both things. All right, closing because of running out of time and I don't want to get killed. Short hint, also always obviously measure what you're doing, right? If you do not measure it, if you do not have your tooling around it, seems to be auto or whatever, you do not know where you improve. But I think most of the people I don't have to tell that. One thing which we have found out, because I'm for some stupid reason start learning about ISO 42010, if you do platform engineering for AI, we can almost set up all measurement activities into this platform. Means that you just have to do, or someone else has to do, all the paperwork and processes, but technically you could be clean for the ISO certification, which you don't have to do, but you have to follow the EU AI Act. And as I said, this is most organizations going to kill because most organizations don't know what to do. But it's active already. So be aware of it. Last but not least, don't over-engineer it. Don't underestimate your resource requirements. The model governments can kill you. I can tell you, if you're continuously playing around, having people left, right, models, whatever, fine-tune a little bit here, put something else there with a rack, it's a mess, right? It's like a kindergarten of people like playing around with Lego and never tidy up. And poor developer adoption is like literally killing the process of integrating LLMs into your products, whether they're internal or external. So turn around the takeaways, take care about find a good balance and control and the flexibility. We always say platform engineering is like a framework, so it's a garden where you can play in. It's standardization. 10 years ago, people would throw me out of the window if I told standardization. Nowadays, you say Kubernetes. People are more or less calm, but this is a standardization engine in the end. Start very simple and slowly find your way into it. Find an efficient resource management. Find out what needs to be literally done. It very varies on your workload, what you're up to, who's your end user, for which cases you're using it. All of it has a different influence, what you really, really need. It's not just like one size fits all. And the first good customer you always will have are developers, because it's in the nature, it's close to their heart. So that's where whom you need to make satisfied, whom you need to make happy, because they are also talking on the coffee machine to your people from, I don't know, marketing, business, product, whatsoever. And if they are convinced, then you can also convince anyone else. Thank you very much. I do not have an end slide, so enjoy the coffee.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.